Two people can see us. Perfect. I think they can. I don't mind if, we can kind of do this informally. If you have any questions, feel free to. It is blank, so sorry. my first slide is empty. All right, so as I was saying, my name is Michael. I'm a software developer based out of Coeur d'Alene, Idaho. Always loved coming over here to Spokane and hanging out with the Washingtonians. And this talk is going to be on C extensions. And basic idea is that C extensions allow your Python code to go ludicrous speed. So the way you can think of Python as a runtime environment is you can think of the Python interpreter as a C program. And what that allows you to do is it gives you hooks, or Python provides you hooks that allow you to hook into the Python runtime with custom C code. So since Python is itself a C runtime, at the end of the day, all of the objects that you're interacting with in Python are actually wrappers around C constructs. And one of the things that we can do as Python developers is hook into that functionality at the C layer and interact. We can interact between C code and Python code pretty natively. So some of the workflows that we do at Crunch involve kind of this process of you write your C extensions with the expectation of being able to consume Python objects in C, and then once you consume them in some sort of function, you translate them into a native machine type that you get down into the C, and then after that you can execute these subroutines on your data in C, and then repackage those results back into Python objects to be turned back to the Python interpreter. So there's this pretty seamless flow between subroutines written in C and code that you write in Python that's executed from the Python interpreter. And what that allows us to do as Python developers is it allows us to push performance critical functionality down into C without resorting to a full rewrite of our app or putting a network boundary off to some other service. So we're going to do a hello world really quick, just to kind of show you how to go from scratch, from nothing, to actually having a compiled C extension that's going to be executed from the Python interpreter. So we're here in a folder on my desktop. We're just going to go ahead and make a new directory, and we'll just call it my package. And then go ahead and cd, actually what we're gonna do is we're gonna open tmux into that, make it a little easier. Okay. And then, okay, so we don't have anything in this package right now. So when you're writing your Python packages, I mean, it's kind of in flux at the moment with PyProject, but .toml. But one of the limitations of PyProject.toml, if you're in Python, is that there's no standardized way of compiling C extensions through that. So you have to use the old setup.py file to do that. So we'll go ahead and make a setup.py file. And then we're going to make a source directory, because that's how we should do it. And then inside that source directory, we can make our my package. Then inside my package, we're just going to make an extension ext and extension.c. That's where our C files are going to be. Okay. So nope, dang it, that's not what I wanted. This is what I get for having two things with my in the word name. But okay, so this is what our setup looks like at the moment. So we have a source directory, we have our package, and then we have our extension.c file. So first thing to note, in the setup.py file, we're going to write it pretty much the standard way we always write setup files, from setup tools. We're going to import setup, and then we're going to import this other object called an extension. And in this setup.py file, we're going to call the setup function and give it a name. It's equal to my package. And then since we created a source directory, we're going to define a package directory to just point the interpreter to actually look in the source directory. And then the thing that we actually care about is this ext modules. And what this is this is a list of extension objects that Python's going to know to actually go and compile for us. So extension modules is a list of extensions. And it usually takes two parameters. The first one's the name, and sorry, I'm used to my old keyboard. So the name is going to be the direct path to the dynamically linked library that Python's going to create. So in this case, it's going to be my package, or actually, yeah. Yeah, we can do my package.hello world. That's fine. So we'll do my package.hello world. So that's going to be the name of this module that we're creating. And then the sources, sorry, I'm used to my old keyboard. Sources is going to be equal to a list of source files that we're going to pass. And actually, I'm going to go ahead and import os.path.
Do you want an external keyboard?
No, it's fine. The problem is I'm used to an ortholinear keyboard. And then let's say os.path.join. You're going to go, and that file is source my package extension ext. I spell it exten extension.c. Okay. So this is what we need in our setup file. We have a name, we have a package directory, and then we have our extension modules, which is a list of extension objects. Okay. Okay. So now with the setup out of the way, we can go ahead and write our extension file. And the first thing that we need to do is we need to import the CPython API. And basically we do that the same way we include everything else. Since Python's going to be handling the compilation of this file, we don't have to do anything in terms of like linking. So if we just do python.h, Python will know what to do. Okay. So inside this file, there are 4 constructs. The first one is going to be the function that we're actually going to write and the function that we're going to execute. In this case, Python always expects a function to return PyObjects. Functions are passed PyObjects and Python functions return PyObjects. Even if the function returns none, it's going to return the none PyObject. So in this case, so when we actually write this, we need to do static PyObject object pointer We'll just call it hello world. In terms of the arguments this function accepts, there's always going to be a reference to the module itself. So there's going to be PyObject pointer self. And depending on if you include arguments or keyword arguments, you would add extra PyObjects to this function signature. But in this case, since we're not actually doing that, this should be enough. Also, I'm going to turn off my LSP because it hates us. Stop. Okay, there we go. All right, so in here, we're actually going to go ahead and include standard.io.h, and then we're just going to call puts hello world. Okay, and then we're going to call it a macro, and just to make things easier, it's going to be py return none. There's a little bit of reference counting and stuff going on behind the scenes that we'll get into later, but for now, we're just going to return none. Okay, so that's the function that we're actually going to call. The next thing we're going to do is, okay, so try to take a step back from this for a second. So what we're doing right now is we're creating a Python module, and inside that module are Python functions that we're going to call. So the Python module is a struct that includes a method table, and that method table is written in C as an array of arrays. So that's what we're going to do next. We're going to write the method table, we're going to inject that into the module object, and then we're going to tell Python to create that module for us, which we'll be able to later import. So that is, we're going to be doing static. There's another object called PyMethodDef. And then we're just going to call it the method table. And it's an array of arrays. It's equal to that. And this array is null terminated, so the last object always needs to be null. And then the last array is always going to be null. And then this array takes 4 parameters. The first is going to be the actual function name that Python expects. In this case, it's going to be hello world. The second object, or the second item in this array, is the function pointer to the C function that we're actually going to call. So we're going to cast this as a PyC function, and then call it hello world. The next is a bit flag that is going to tell the Python interpreter what this function expects. There are several that we'll get into in a little bit, but for now, since this function doesn't expect anything, the bit flag is called meth no args. Pretty self-explanatory. And then finally, there's a 4th parameter for a doc string. You can include none, but in this case, we're going to say prints hello world. From C. Okay, so that's the method table. The next thing that we need to do is actually create the method object, or the module object that this method table is going to go in. So the way we do that is we're going to call static py module def, module def, and then we're going to call this extension, XTNION, and this is just a struct. And so there are a few things that you need to include with this definition. The first one is always going to be py module def underscore head init. It's just a macro that actually does some initialization for you. And then there are 4 other parameters that this takes. The first one is going to be m underscore name. And this could be the name of the module. And we'll just kind of call this hello. Actually, let's call this what do we call it in? Yeah, we called it hello world in the setup file. So we're going to call it that too. Hello world. Next one's going to be mdoc. And this is going to be a documentation for the module, the hello world module. Next one is going to be msize. This is only relevant if you have to deal with subinterpreters, which is like a very niche concept. Actually, it might not be niche now that they pushed the GIL to be per interpreter, but for now, we're just going to set it to -1 because we don't care about it. And then the last object is going to be, or the last tag in the struct is going to be methods, which is going to be equal to the method table. Okay, so that's the third thing. And then finally, there is a py mod init func. And this is a macro that is actually going to tell the Python interpreter to actually load this library or load this module. So it's the way you structure this is you're going to go py init, and then underscore, and then your module name. So hello world. And this is a function. And the only thing that you need to do here is return py module create. This is a function in the C Python API, and you pass it a reference to your extension. Okay, so this looks good. Okay, so it's 4 parts here. First one is the function that we're actually going to call. The second part is the method table that is the list of functions that are available for the module that we have. The third thing is the module definition itself. And then fourth is a function that actually loads the module into the Python interpreter. Okay, so let's go ahead and go make a virtual environment. Yeah, what's up?
So on the last screen you're on, the top, you have your method itself that you're talking about, and then your array.
Mm-hmm.
Let's say you're making this extension and you wanted it to have different methods. You would list all those up top, and then when you get to your array, you would list each one of them out.
Yeah.
And then the other 2 pieces would stay the same, basically.
Basically, yeah. Okay. So if you wanted more functions, you just add them here. Yeah. And yeah. So, cool. so that's just for functions. If you wanted to create your own objects, which I'll show you an example later, there's a different way to inject that into the module. But just in terms of like methods on the module itself, those are the functions that you define in this method table. Okay, so now the question is this thing going to install or not? Okay, so ideally, let's go ahead and activate our virtual environment, VBA, and python-m pip install-e local. Okay, that looks good. Okay, so what this should have done, if everything looks good, is, okay, so what we did, so basically based off of the extension that we defined in our setup file, it went ahead and built this hello world shared object file. You can think of that as like a DLL in Windows. And this is your compiled extension. And what we can do is, now that we have our virtual environment and this is installed, why am I using 3.6? Okay, whatever. We can come in and import my package. Cool, that looks good. Package.hello world. Okay, that looks good. Actually, let's just do, sorry, one more thing. Just make it a little easier. Hello world as HW. Okay, so here's our module that we actually went and created. So it's saying module my package.hello world from Michael code Python package, and it's pointing to that shared object file. And this is just a module like every other module, so we can do things like, you know, look at the dictionary representation of it. That's what I want. So as we can see at the very end of this list, you have that hello world function. So if we do hw.hello world, voila. Okay, cool. So what we're doing here is just to put a point on it. So we're inside the Python interpreter. We just called a function that is written in C, and the Python interpreter loaded that dynamically linked library into the runtime and then executed that function for us. And so that string hello world actually came from that puts call that's down in your C extension. Okay.
15 minutes.
Cool.
That's pretty solid.
Yeah,
Okay.
crazy.
All right, we're done.
No, okay. So just to put some of the highlights up on the board. I might have written this backwards. So if you're thinking from the bottom up, there's that pymod init macro, which defines the internal name, and I can send you all the slides and everything if you want, if you don't want to take notes. So there's that macro that defines that allows you to define a function that will actually load the module into the interpreter. That calls the PyModule create, and it takes an address to your PyModule definition. And then PyModule definition is a structure, is a C struct that defines your model parameters and includes that method table. The method table is a struct that maps function names to call in Python, and it's null terminated. And then some of the other flags that you have available for those function calls are meth no args, meth object, meth var args, and meth var args bar meth keywords, and those are for no arguments. If you have one argument that's an object, you have variable arguments, and you have variable arguments with keywords. So it'll either pass like one object, a tuple, or a tuple in a dictionary. Okay. I'm kind of doing this out of order. One of the things that you can do with C extensions is use debuggers. I don't know how many of you typically do your Python development using debuggers like PDB or PDB++ or something like that. But one of the things that I've found when writing these C extensions is that workflow pairs really well when you debug your C extensions using GDB. GDB requires an executable, which in this case is going to be the Python interpreter itself. So instead of like using like scripts that you can have loaded when you install Python, you need to call the module itself. For example, like when you go ahead and install PyTest, you can either call PyTest directly, and then your environment knows how to go and find PyTest, which is going to be an executable that's going to tell Python to execute it. Or you can execute the module itself by doing python-m PyTest. And what that gives you is it gives GDB the ability to use Python as the executable, and then that instance of Python is going to go ahead and run PyTest. The nice thing about this is when you're doing test-driven development like this, you get PDB for your Python code, and then you get GDB for your C code. So you can actually set breakpoints in both your Python code and your C code, and you can kind of have that similar workflow when you're working with code that's written in Python and code that's written in C. So if we wanted to do this, for example, we can go ahead and exit this. Go ahead and actually let's go ahead and make a test directory, because it's always a good thing. And then inside that test directory, we'll go ahead and add a test extension .py, and then we'll just dang it, I was looking at the TV again. Def test, just test printer, why not? And then inside this test function, we'll just do hw.hello world. We'll just call it. And just for fun, we'll throw a PDB in here, just for kicks. Yeah, keyboard. Okay, anyways. So, a few things to note. When you're debugging C extensions, what you want to turn off optimizations that the Python interpreter is going to implicitly use for when they compile C extensions. And the way you do that is you pass an environment flag before doing a compilation step. So that flag is called C flags. And we're going to pass the argument -0 or O0. And then one of the things that you can do with Python is you can call that setup file directly, and one of the arguments that it takes is build extension ext. We're going to build it in place, and we're just going to force it because we do that. Okay, and what that's going to do is it's going to allow, it's going to compile your extension with those debugger flags and those hooks that something like GDB is going to use to find your objects. Okay.
So is that -0, basically like?
No optimizations. Yeah, I think it defaults to like 03, which is like the most optimized it can be. But if you pass cflags -0, it'll leave all of those. It'll compile it in a way that GDB can actually like show you stuff instead of like optimizing stuff out, objects out.
I know without CC flags.
Python is a great C framework. You know, if you think about it. Okay. Oh, we're not going there. Okay, so let's go ahead and, okay, so we compiled that, whatever. We'll go ahead and run gdb-args, hang on, actually, I need to install pytest first. Python-m pip install pytest, since I have a virtual environment installed. Just gonna let that run. Okay, so the way we do this is gdb-args, python-m pytest, because GDB needs that executable, and that's going to drop us into GDB, and then let's just put a breakpoint on that puts function, and then run it. So here's PDB in the stack trace from Python. As you can see, we put one in before we actually did that function call. So you know it looks like the GDB debugger, you know, beforehand. You can go up the stack trace, down the stack trace. I don't know how much you guys work with PDB, but I tend to use PDB and actually PDB++ a lot when I'm at work. So that's PDB, and then we're going to hit continue, and then that gives us, now we're in GDB. It looks very similar. If we go to frame 1, this actually gives us our object in scope in the C extension. So some of the things that we can do is we can look at the self object. There's a pi object right there. We can dereference it to see what it is. There's just things that you hear about in Python like reference counting, and then there's the OB type, which is the module type, and it's just kind of fun to play around in these like little sandboxes. And you know, these are the kind of C structs that Python is handling under the hood that you have access to in your C extensions, but you don't normally see when you're writing Python.
I'm not sure I quite followed how in GDB and it moved to drop into PDB.
Okay, so since GDB is running the Python interpreter, the Python interpreter is dropping into PDB. So you have the context of your interpreter state in PDB, and then GDB will also break on your C code when the Python interpreter actually executes those C functions. Okay. So that's how that works. Okay. So there's that. Okay. So some of the typical workflows you see when you're working with C extensions is that you're taking Pi objects and then you're deconstructing them to some sort of underlying C machine type, and the C Python API provides functions to allow you to do that. All Python objects have a corresponding Pi type as from type, which will unwrap. Like for example, if you're looking at an integer in Python, those are represented as long types in C. So there's a pi long from long. And what it's going to do is it's going to pass you a long object. Actually, I wonder if we can just do that. Why not? We're just having fun here. And then run, continue, frame 1. Okay, so we should have access to the Python interpreter. I'm not 100% sure. So pi long from long, and then we'll just pass it a 1. And there's a Python object for us. So what this did is it took the value that we gave it. It's probably an int, but it cast it into a long type, and then it wrapped that into a Pi object pointer. And actually, it might be giving us one of the objects that the Python interpreter has cache. I think it's like 1 to 256, like they're like have like immortal objects. Like instead of creating a bunch of ones everywhere, like there's only one object and everything's just a pointer to that one object. So that might be that one. Actually, we could probably find out. Do we still have this in cache? Yeah, we do. Let's just dereference it. Yeah, okay. So this thing has like 1,800 references to it. So that's, yeah, it's obviously like it just gave us a cache version instead of like creating one on the fly. But you know, you don't have to worry about stuff like that when you're dealing with the CPython API, and most of that stuff's handled behind the hood. Okay. Some of the things that you can also do is your functions can take arguments and keyword arguments. There's a pyarg parse tuple and keywords function that will take a tuple object, a dictionary object, a string representation, and you can just look the string representations of how Python will expect an object to be translated into a C type. Those are available in the Python docs. And then a keyword list to designate which values in the function call were actually keywords, and then references to all the pointers that you want filled out. So for example, this function right here, oh, I must not have updated that. Okay. Anyways, I could probably actually find an example somewhere. Yeah, I got one. Okay. Here, we'll just look at one in action. Lazy CSV source. Lazy CSV. Let's see. Okay, here's an example. We can talk about this module a little more in length later, but so when Python's going to call this is actually a constructor for an object. So when it calls this function new, it's going to give a type. It has a Python object, which is a tuple for the arguments, and then a Python object, which is a dictionary for the keyword arguments. And then what you can do is you can create a list of keywords that you expect for someone to pass through this API, and then pointers to all of the variables that you actually want unpacked. So in this case, it's going to be an object. Everything else is optional. A string, a boolean. I don't remember what the n is, but another string. So that's how that works. But just in terms of the general overview, you have the ability, but the CPython API provides you functionality that allows you to take objects, like consume Python objects from the Python interpreter, and then actually parse that out into individual like C types or other Py objects that you can use later. And then the inverse of that is this function called pybuild value, which takes a string representation and a bunch of values to C data types, and then it'll actually wrap Python objects, and then it'll return that to the Python interpreter. Okay, memory considerations. So as we saw on some of those examples earlier, Python uses this concept of reference counting, and it uses reference counting as a means to determine when an object that's available in the interpreter needs to actually be freed from memory. All Py objects are heap allocated, and there are macros included in the CPython API for increasing the reference count and then decreasing the reference count. So when you're writing in C, you need to consider the fact that you are being path referenced, and if you save or you have to recognize that you're handling memory allocation by yourself. So there are some functions that will give you what's called a borrowed reference, which is a reference to the object, a pointer to the object in the Python interpreter, but it didn't increase the reference count. So if you want to keep that reference, you got to increase the reference count. And then conversely, there are functions in the CPython API that give you an owned reference. And an owned reference, what that is it's going to give you an object that has an increased reference count. So if you want to delete that object, you got to decrease the reference count yourself. So, and if you don't do this properly in your C extensions, it results in either undefined behavior because it's going to free an object that you still have a pointer to, or you have a memory leak where you have an object that you created that has a reference count but is not actually referenced anywhere. Let's actually look at an example for that before I get into defining new types. So I'm not going to do this one by hand because that was stressful enough as it was. So I have a second library called myStack that goes ahead and this laptop has in it the, stop, shut up. Has in it the implementation of a stack data type. You know, stacks are these objects where you can push items to the stack, you can pop items from the stack, and you can go up to some number of items on the stack, and you have a length associated with it. You know, it's your first in, last out data structure. So obviously, one of the things that we need to consider when we're creating a stack type, a type that is a collection of other types, is what do you do with those reference counts as you accept and as you push items to the stack and then you pop items from the stack. So this object has two functions associated with it: stack push and stack pop. The first one is the flag method object because there's only one object that you're pushing to the stack. And then the pop doesn't accept anything because you're expecting to get something from it. You're not actually pushing, you're not actually giving it anything to use. So let's look at this. Let's look at the stack push one first. So this function stack push is going to take an argument of itself and then a pointer to the item that you're pushing to the stack. You increase the length of it by 1. You have to reallocate the memory that the stack has available to it to actually store these pointers. And then you want to increase the reference count to the item because the stack is being given an item to store. So the stack owns a reference to that object. So you need to increase the reference count to this. If you didn't do this, that object might be freed and then you go to pop the stack later and then you're giving off a pointer to something that doesn't exist. There's a problem. And then conversely, actually, this is actually kind of funny. The inverse of the push is the pop, but you're actually passing off that reference to someone else that recalled for the pop. So in this case, you don't actually need to do a decrease in the reference because what the stack is doing is the stack is giving up the reference to the object that it had. So when you're pushing stuff onto the stack, in this case, you need to increase the reference count because the stack owns a reference. And then when you pop that thing off the stack, you're usually doing an assignment of saying this object is assigned, stack.pop. So we're passing off that reference to something else. So we don't have to worry about for decreasing the reference count on that.
So that would be like one item on your stack, and then you popped it.
Yeah, so
to 2 reference counts, that you would still just have 1.
So the model is here. Let's do I have a virtual environment of this? Yeah, let's just do it. From stack import stack. Dang it. I'm over my skis here. I'm in the wrong. All right, obviously I didn't check this code beforehand, but it's not compiling the way that I wanted to. Okay, so the question is about reference counting. So we can do this in terms of a list. So let's say I have let's say I have an object x is equal to 1. So the reference, one is a bad value option. Let's say let's do 257 because I know that one isn't cached. So there's only one reference to this object, 257. So if I were to come here and delete it, it's not going to find the name, and the 257 is going to be deleted. So there's one reference to that. If I were to pass this, object X off to my stack object, assuming it was compiling, I don't know what's wrong with it. X would own a reference, and then the stack would own a reference. So the reference count of 257 would be 2. Okay. So now imagine that stack object is now you're going to call the pop method off that object. So it has a reference to this 257 value, and the way that would be annotated would be, it'd be something like y is equal to stack.pop. So it's not that you're losing a reference here, it's that you're passing the reference off to this y variable, or in this case, you're going to be passing it off to the interpreter, and then you should.
When you do that, Python isn't automatically creating a new reference because y is pointing to that value.
You don't have to delete the reference because the reference is being passed off to the y, to the variable. So, okay.
What happens if you just discard Bob? Is it the same sort of right for deal, or?
It should clear up. I wish I had this. I wish I had this working. Otherwise, we could try it. But I'm pretty sure at the end of the day, it's going to. I don't remember off the top of my head. I'm pretty sure we're not leaking anything here. Anyways. Okay, so the last thing I wanted to touch on is actually going about and creating new types in our C extensions. So we can create entirely new Python objects using the CPython API, and then on those objects we can define attributes and methods that are also written in C, and then the Python interpreter will be able to invoke them. They look pretty similar to what modules look like. But with some differences, and we can get into an example that actually works, that demonstrates that. So the way object representation works in C, since C is not an object-oriented language, is that and we saw this earlier, we had a pointer to our Python object, and that Python object had a struct tag called obtype. And what that is a pointer to the type of the object, the type definition. And inside the type definition is where all of your functions are listed. So you kind of get a glimpse of that when you're working with Python. You know how you can, like, if you have a list object, you can call the methods on it by saying, let me just. We can call x.append to. That's one way that we can call this method off of a list object. Another way that we can call it is list.append x2, because instead of calling the object itself, we're going to call the type. And that's what Python's doing under the hood. It's actually using the reference to the object, getting a pointer to the type definition, and then on the type definition is where all the functions are defined. So that's why we can do this, and then we have 2 objects, or we have 2, our list is of length 2. So you see kind of similar paradigms between what's happening in Python and what's happening in C. Where was I going with that? Okay, yeah. So how this relates back to C extensions is that we actually go through and define the PyType object, and on that PyType object is where we list our functions or our methods for that type. And then when you have an object in the Python interpreter, it's going to do that same thing of it's going to call the function based off of the type, which is being pointed to by the instance of the object. So to kind of demonstrate that, I have one more library. Let's go ahead and exit this. We can exit this. That was sad. I have one more library that's called Lazy CSV, and this is actually a library that we worked on at my job at Crunch. And this is probably a more fleshed out. Actually, let's go ahead and get out of. That's probably why it wasn't working. Let's go Lazy CSV. Go ahead and create this. And then Source lazy CSV.c. Okay. And we can zoom out a little bit. You all see that still? A little more in, further in. Okay, cool. Okay, so we're gonna start at the bottom. Ignore all this NumPy stuff. So pretty similar approach. We have that pymod_init function, which is the macro that actually goes and loads the object. The only difference here is that we're doing a pymodule create of the module itself. I think I mentioned this the last time I was here. Python represents errors as returning null values, and that's a global error state. So if you ever see a return null, that means an error happened, and to basically just jettison. And then the next thing that we're going to do is we're going to call this pymodule add object, and this is where we actually pass it a reference to the type definition that we have. Did that work? No, that didn't work. Okay, and this is the type definition. Similar flags. Some of them are similar. You have a name. You have a document. You have doc. You have a basic size. A lot of this is just documented in docs.python.org. They have a extensive section on C extensions that you can look at. The two things worth noting here are there's methods and then the methods are the functions that you define off of this object, and then the members are like instance attributes. So if you had a dot, let's go ahead and actually I have a test suite, so that'll make it easier. Let's go here. This sounds like a good place to hop in. Okay, so right now, in this test function, we have this lazy object, and that is an instantiation of this lazy CSV type. And if we do dir, oh, it was vars. That's what I was doing. If we look at the dictionary representation of that, if I can spell. No, it doesn't have a dict attribute. Okay, lazy. Some of the things that we see defined on this object are calls, headers, name, row, and sequence, and those correspond to the methods and the members on this type. So methods is actually a method that you will call on the object, and then members is just like an attribute that you can see on the object. So in this case, lazy.rows is equal to 2, lazy.calls is equal to 3. Just a little bit of backstory. This lazy CSV library is a memory efficient CSV parser. Basically what it's doing is in C, it is building memory mapped files. It's taking memory mapped files and indexes and allows you to extract CSV, sequences of CSV from a CSV file without instantiating any of that in memory. So it uses the iterator protocol to say if you had a file of, for example, 2 rows, 3 columns, you can create an iterator for like the 3rd column or the 2nd row, and it'll lazily yield you data off of that object. And that's all written in C. So that's what I mean by like rows and columns. Those are rows and columns of a CSV file.
So like a really big CSV file, you would never have the whole thing in memory.
No. Because that's always a problem for us at Crunch because we ingest a lot of CSV. Last thing I heard was our profiles data set was like 1.4 terabytes of a CSV file. So that thing ain't fun to parse.
Single CSV file?
I don't know. I don't know, man. We do some crazy stuff. Okay. We are looking into Parquet, but this profiles data set is old and it goes back years and years and years before Parquet even existed. So that's nobody's touching it. Okay, so All right, where were we? So we have methods and we have members. Basically, members allow you to define like just attributes off of the object, and then the methods are the methods that you can call. Yeah, I think that was it. So just to kind of wrap this up, defining new types, you basically at the very end of your type definition, you would call this my PyModule add object, and then you would add a pointer to that object type. And that's how you do that. That's all I got. So thanks for attending, and if you have any questions, let's fire away.
Can you repeat questions? So
Yeah, go for it. Yeah.
So after, it's like, what would be a good example of a speed increase that you saw from actually taking something that's traditionally written in just Python and then converting it into C and then
Well, we had both speed and memory increases just based off of, because the way that we were initially, so when we came out with, so what we use the lazy CSV for is business to business integration pipelines. So we have third-party APIs that we call, they send us a CSV, we have to parse it. Our internal database is column oriented, so we need to take that CSV file and then parse out the columns for that file. Originally what we were doing was we were doing that in pandas. Pandas has a lot of memory overhead. It's very slow. It's not the tool that's it is great for getting you off the ground and getting you to version 0.1 really quickly, but it's not the tool that you need for the job. So step 2 was to be able to come in and say, okay, we can take out pandas and sub in something else. We wrote a Python implementation and some Python of this library. And that gave us some good performance benefits, but it also introduced some memory overhead. One of the problems that you have with when you're indexing, so the way that this thing works is it actually goes through and indexes the whole file, and it basically gives you the ability to say, okay, I want the 3rd row and the 4th column, and I want the value in that field. So one of the problems that we're running into with that implementation was actually memory based, because if you think of a CSV file, each letter is just an 8-bit character, an 8-bit character under the hood. But if you start generating numbers that represent characters in this file, of course, okay, so worst case scenario for a CSV file is an empty CSV file. So you just have all commas. So each comma is its own index. But if your files get too big, so for what was the number I was using as an example? 65,000 something. Well, you need, what, 4 bits to save an index value for 1 bit of a file? So your index is just like blow through your memory. So one of the things that this thing does is actually it restricts the index to a U16 type, and that was one of the major benefits that we were getting out of writing in C, because you kind of need to be pretty close to the metal in terms of actually doing proper memory management and making sure that you can like really optimize your subroutines and your protocols to A, be as fast as you can, and B, be as memory proficient as you can. There's actually let's see if we can find this. I don't remember that off the top of my head. If you remember back to your algorithms and data structures class. Give me 1 second. Where is it? This thing's kind of big. Iter as list from. It's been a hot second since I've looked at this code. Value, that might be it. Value from value. This is what I'm looking for. Okay. Anyone recognize this algorithm? It's a binary search. So what we did was we were indexing values in a CSV file, but once you got up to a value that was greater than a U16 type, we would drop a second index for where that happened. So we were able to say, like, if our indexes were like 1, 5, 7, 16,000, then at some point we'd be able to drop back down to 0 and again keep indexing up again. But in that, so that gives you 2 indexes, but you have to be able to search for the value that you're looking for in the index. And since they're already sorted, you just do a binary search to find the actual value that represents the bit in that CSV file that points to the field that you're wanting to read. So if you have a second index that's just a bunch of random numbers, you don't know the length of it because you don't know the size of your CSV file. But you know the length of the other one because, you know, if you have like 5,000 rows, okay, that should be 5,000. You know, there should be 5,000 values in it. So you have to do a binary search on the invariant one, and then you can index into the one that actually points to the where in your CSV file your data actually is. So the real benefit, so we did have speed increases. We did have performance benefits from rewriting in C. I think we went from like 2 days to down to like several hours in terms of ingesting CSV files. But the real benefit here was the memory footprint, especially for those indexes.
How do you how should you go about adding type-ins?
Oh, there are no type-ins here. I don't do that.
Possible?
And C,
We should use like type sheds or something.
no idea. I'm not. We hardly do any type-ins at work.
You only have 3.6 installed.
Yeah.
Maybe not.
We kind of have an older version, or we're still running off an older version at work. But yeah, we don't do that here.
This is went one way now.
I mean, Steve's typed, so there you go. I mean, you know, you have that problem where, like, okay, you assign a value, what is it, UN32 type, you recast it to a character pointer, and now your value is an array, you know, whatever. I don't know. But yeah, in terms of Python, like, I don't know. I don't know how that interacts with MyPy or any of your static type analyzers.
Gotcha. Have you guys done any, like,
There
or anything like that?
There is a library that allows you, there's a library called Pyo3. I've dabbled around with it, but the nice thing about C extensions is that it comes with the interpreter. So you don't have to install Pyo3 or add an extra dependency to leverage C code directly in your Python code. You know, it's just there. It's just it's available for you to use. I mean, Rust is great. I love writing in Rust, but in terms of just friction, in terms of like adding extra packages to your company repository, if you can write in C, you know, I personally think it's just write in C. So
Thank you.
C's fun. I don't know. So.
Where can people go to like learn more about this? You mentioned the Python docs.
Okay, yeah, we can go over that. Let's see. Let's say I don't remember exactly what that function pylong from long site docs.python. This is usually the easiest way to go. Well, it usually is. What's wrong with it? There we go. Okay. I'm wrong with it.
This is the first time you used your mouse in the last hour. Really aggressive. I've been watching it on the screen.
Well,
New event for everything? Or
huh?
do you use new event for everything?
Yeah. I like having as minimal overhead, like abstraction as possible when I'm writing. So like I like using the terminal. I just like using a TUI, like NeoVim. I like just using debuggers straight from the Python interpreter. You know, once you start adding like, what's the word I'm looking for? Once you start adding a TUI on top of a GUI on top of like VS Code and cause of like, you know, you start getting so far away from your program and it's like, okay, what's actually broken here? I don't know. So I just like to kind of keep that as minimal as possible. Okay, but in terms of documentation, the CPython API reference manual is great for getting started. It talks about like macros and exceptions and stuff like that. And then you can also just go in here and search like if you're curious about how tuples work, for example, tuple. It's usually you're looking at something like pytuple. There's functions like pytuple new, which here's an example of how we're talking about how a function might give you a reference versus a function might give you a borrowed reference. The documentation will tell you whether or not, okay, so if you call this function pytuple new, you have a reference to this object, you need to make sure it's freed appropriately. So, and the documentation kind of goes through all of that. Beyond that, I just kind of like hacking away at GDB and in my terminal just to kind of see what works. Like I showed. If you compile it without any of the optimizations, you have the API there available. You can just kind of like type things away and you can call stuff through GDB. And that's just my preferred workflow, and I'm just used to it because that's how I do my Python work as well. So yeah, docs.python.org/3/CAPI is the root of this documentation. So.
Could you touch briefly on like the ABI? I feel like that's something that's not a lot of Python developers aren't super familiar with, myself included.
Probably not.
Okay.
It's like the application binary interface. Is that like the bytecode that it compiles down to? I'm not entirely sure.
Like, there's some level of guarantee that it's going to be the same from like version, but it's different than like there's sort of like two levels of like Python's breaking changes. But I don't know too much about
I'm not very familiar with that. What you're saying definitely rings a bell, but I've never had to consider it when I'm writing C extensions.
That's good.
So I'm not saying that's a good thing. I'm just saying that that's my experience. So. Anything else? Cool.
Awesome.
And that was an hour.
I will end
Nice.
the online stream. Thank you.
Yeah, happy to do this. It was fun.
Sweet.